Hey, and welcome back to SanfordFlipMath. This is AP Calculus. We are deep in the throes of the derivative chapter, talking about how to take derivatives, and actually in this section we are going to move into why would we bother to take derivatives. We are working in the Finney, Demana, Kennedy Calculus, Graphical, Numerical, Algebraic 3rd edition, just so you know where some of this comes from. And these definitions come from Chapter 3, from the pages that you see here in the Finney, Demana, Kennedy book, again, calculus book. So thank you to them. And basically, these are just photos from the book. We're going to talk about some applications of derivative, specifically velocity, acceleration, and a couple others that are related. Okay, and so with that in mind, let me just remind you of a couple of things. We've talked about average rate of change, and that's obviously not derivative. That is slope, like back in Algebra 1. And we've already spent some time talking about instantaneous rate of change, and we've even done some examples of that in terms of like, let's say if we're talking about instantaneous rate of change, we're talking about rate of change right now. An example of that would be the rate of change of distance, also known as velocity. Like if you're driving in a car, if you're looking at your speedometer and your speedometer says 57 miles an hour, that means we're driving 57 miles per hour right now at that second. That does not mean that on average we're doing 57 miles per hour over, however many hours. Okay, so instantaneous rate of change is, again, rate of change right now. It is also known as derivative, really. And let me just kind of remind you of some synonyms that we've already mentioned. And those synonyms include instantaneous rate of change, slope of a tangent line, slope at a point, velocity at time, at some certain time, slope of a curve at a point, again, derivative y prime by f prime, dy dx. I'm going to make a tiny little adjustment here. It's certainly related to speed if we ignore the direction issue. And so it's pretty close. Okay. All right. So I'm just kind of summarizing some of the stuff that we're going to be playing around with here. Instantaneous velocity, again, excuse me, is a synonym for derivative. So if we are talking about some curve that's, s of t, in other words, and I really don't know why s gets used. Probably because we don't want to use d. And this is basically just a distance at time, at whatever time we're talking about. Okay. Probably don't want to use d for distance because of all the dy dx, ds dt, all that kind of stuff. Okay. So this is the same idea as dy dx. It's just, if the function is f of t or f of x or f of something, then it's going to be df. And we're talking about time as the independent variable instead of x. Okay, so velocity is basically just derivative of position. Okay, so if you have a fixed velocity, the derivative is just going to be whatever that velocity is. Okay, if you have a fixed distance, the distance that's not changing, then the velocity is going to be 0. Okay, so if I have something like the position is given by, let's say it's 5t. Okay, well, s prime is just 5. So here's the thought. Maybe time is in seconds, and maybe this is in feet. Well, if that's true, this is going to be feet per second. It's like a speed. It's just this is how fast it's moving. Okay. All right. Speed is very, very similar, and the only issue is that speed needs to be the absolute value. So, like for instance, if I'm driving in my car, or my truck or whatever, and if I'm going forward at 25 miles per hour, then my speed is 25 miles per hour. Okay, nothing earth-shattering about that. Well, if I'm backing up at, let's say, 5 miles per hour. Well, backing up ought to imply a negative since I'm going the other direction. Well, so that'd be my velocity. Well, my speed is just going to be 5 miles per hour. So what we're doing, I was backing up 5 miles per hour. Well, how fast is that? 5 miles per hour. Isn't that deep? Okay, so just do the absolute value. Okay, and really that's pretty much it. Okay, acceleration is the rate of change of the rate of change. Okay, so if that's true, then the acceleration, okay, so here's the rate of change of velocity, the rate of how fast is velocity changing. So it is the derivative of the derivative, which we typically actually in calculus verbiage talk about the second derivative. That means do the derivative, take that answer, do the derivative again, and this is the notation, and sorry, but that's not a typo. That is d2s over dt squared. It is the second derivative, and the notation looks like that because of this. Here's with respect to t, and I'm doing the derivative of ds, so that there are 2 of those d's, but not 2 of those s's. There are 2 of those dt's, okay, and just understand that it means that dt. Now, technically this is not multiplication, but since the notation looks so much like multiplication, that's why they just continue on with that same kind of notation. All right, let's just do a quick speedy example here. Let's say I have the height of a given object that is moving up and down. So let's say we launch a ball, it goes up and it comes down. Okay, maybe it's cleverly out of a cannon or something, and we shoot it pretty much straight up. Okay. Let's say it's following the equation negative 16t squared plus, let's launch it out at 50 feet per second, and it's coming from an initial height of, let's say, 3 feet. Okay, this negative 16 comes from half of negative 32, which is the acceleration due to gravity in feet per second squared. Okay, and for all of you physics folks out there, you're going, oh yeah, yep. And if not, then that's okay. I just told you what it meant. All right, so this is the height at any time that I put into this. I want to know the velocity, which is, you guessed it, the instantaneous rate of change of height. How fast is it going? Okay, so I'm just going to do derivative. So 2 times negative 16, 1 times 50. Okay, and this exponent goes to 0, so there's no t there, and the derivative of a constant is nothing. Okay, so what that means is I can find out what the velocity is of this thing at any time I want. So for instance, if I want to know the velocity at 1 second, so that's a second after it launched, I just do negative 32 times 1 plus 50 is 18, and this is feet per second. Okay. If I wanted the velocity after, let's say, 2 seconds, then it's negative 32 times 2 plus 50 is negative 14 feet per second. Okay, so what is the significance of that negative? Well, that means it's going down now. Okay, it's pointing down. So this thing went up, and on the way up, 1 second in, it was going 18 feet per second upward. Then on the way back down, it was going 14 feet per second downward. Okay, so just a quick little reminder then. If I wanted to know the speed at 1 second, speed is 18, you guessed it, feet per second. If I want to know the speed at time equals 2 seconds, then it's the absolute value of negative 14 feet per second. Okay? So velocity is the derivative. All right, hang on. Let me do this. And I'm going to grab all of those guys. Let's group them together. and scooch them down out of the way. Let's extend some more, scooch them down out of the way. I don't really need them right yet. Okay, back up. Sorry, they had to see that. I should have paused. Okay, so back to the same equation that we were just working on. Okay, so the height is given by negative 16t squared plus 50t plus 3. Okay, I want to know, okay, so I just found velocity and speed. Okay, now I'd like to know the acceleration. Yeah, you were watching my handwriting. Well, acceleration at time t is the derivative, basically it's h prime of t prime. Well, that's kind of notation. Sorry, I did actually just make that sound. Sorry. So in other words, we're doing the derivative with respect to time of h prime of t. Now this is a boatloaded notation just floating around here, but basically we're just going to do the derivative of what we just had. Okay, so I'm going to take this guy right here and I'm going to do the derivative. Okay, so this is h double prime, and you can write two of those little apostrophe looking guys there for double prime, prime prime. Okay, the derivative of negative 32t, well, this is a 1. 1 times 32, negative 32 is negative 32. Sorry, that's not a 2. I was thinking about t. Negative 32. Then t to the 1 is going to become t to the 0, so I don't need to write it. Derivative of a constant is 0. Okay, so this is it. This is the acceleration at what time, though? Well, if I want to know, let's say I want the acceleration at time 1 second. So I know it was going 18 feet per second upward at 1 second. Well, guess how fast that was changing? Well, it was changing negative 32 feet per second squared. It was changing negative 32 feet per second. The velocity was 18 feet per second, but it's decreasing on its way up. If you think about it, as this thing is shot and it's going up, it actually goes slower and slower and slower and slower and slower. And then it starts falling. And then the velocity is becoming negative, negative, negative. Okay, so it's going up, and at some point it decides to start coming down. Okay? Well, the acceleration at time 2, well, it's also negative 32 because it's constant. The acceleration for this sucker was constant. So every time a second goes by, it's decreasing by 32 feet per second, the velocity is. Okay? And that's a constant change of its velocity. Okay? All right. Let's move on. Let's do some more. Okay? It's magic, I tell you. So here's the situation. This is borrowed from page 136, number 8, again from our calc book, Finney, Demana, Waits, Kennedy. And the problem says, and you can look in your book, the number of gallons of water in a tank, t minutes after the tank has started draining, is Q of t equals that equation. So that equation, the answer to that equation is the number of gallons in the tank, and t is the number of minutes. Okay, so this tank is draining, and at time equals 0, if you wanted to know how much was in there, you'd just put 0 here, and it'd be 200 times 30 squared, so 200 times 900, which is 18 something or 180 something. Okay, all right, that'd be how many gallons are in there. What we want to know is if we wait 10 minutes, at 10 minutes in, how fast is the water coming out? How many gallons per minute are actually coming out? Because this could be changing as we go through the process. Okay, so how fast at a specific time is instantaneous rate of change, also known as derivative. So that's what we need to do. We need to do the derivative of this beautiful equation. Okay, so in other words, I need Q prime. Okay, so we're going to do the derivative, but the problem is the derivative, you know, how am I going to do derivative of this? I personally don't like this form. Either I'm going to have to know something about the chain rule, which isn't in this section yet, that's not till section 6, or I'm going to have to change the format of this. So this is still Q of t. This is not derivative yet. It's 200 times, well, 30 minus t times 30 minus t. Now some of you are trained professionals at doing this in your head, and you are welcome to do that. Or you can play along with me at home. Now we can distribute the 200 or not. It doesn't really matter because you could do the derivative first and multiply this number by that. I'm just going to go ahead and write it all out. So this is 18 with 4 zeros, so 180,000, minus 12 with 3 zeros, plus 200 t squared. Okay, this is, again is Q of t. This is not the derivative. I haven't done the derivative yet. This is just Q of t. Okay. I don't know how much of this. Oh, awesome. Watch this. Mrs. Sanford being sneaky like a mug. All right, so this is Q of t rearranged. And if you need to go back and see where that came from, you can pause, you can rewind. This is the beauty of flipping the classroom. All right, Q prime. All right, so the derivative of 180,000 is 0. Okay, I don't really need to write that, but this derivative is 0. Okay, there you go. Okay, now, the derivative of this guy, well, t to the 1 times negative 12,000. I think I had a bonus 0 there. Sorry about that. Okay. Well, and this is t to the 1, so when I subtract 1 from that to do the derivative, this then becomes t to the 0, which means it's not there. And then this becomes, the 200 becomes 2 times 200 is 400 t. This is derivative. This is instantaneous rate of change. Now, if I want to know how fast is it draining, what is the instantaneous rate of change at 10, I just need to do Q prime of 10. So this is negative 12,000 plus 400 times 10. So that's negative 12,000 plus 4,000, which is negative 8,000 gallons per minute. So a couple of little questions here. What did we just find? We found how fast whatever this water is coming out of this tank. And then the question I have is, why is it negative? If the volume of the tank is decreasing, then the rate of change had to be negative. Okay, so that just confirms the fact that the water is draining out. Okay, so imagine I don't know what shape this tank is, okay, but I have water in there, crystal clear blue water, okay, and as the water is draining out, so I have some little spigot down here on the bottom with a little turn handle, and as the water is draining out, the level in the tank is going down. Okay, so it was here, now it's here, now it's here, now it's here. So the amount in the tank is going down, it is decreasing, so the rate of change is negative. Okay, the slope is negative. Okay, one other little note here. This question does ask what's the average rate of change during the first 10 minutes. Okay, I'm not going to do that part of the problem here, but I do want to mention how it would happen. Remember that average rate of change is like old school slope. Yeah, that didn't work, did it? Let's try again. Slope. I know that's bugging somebody right there, that little guy right there. Sorry. Okay, now it's bugging me. Okay, yep. 10 seconds wasted on this silliness. All right, sorry. Old school slope. So if it's over the first 10 minutes, you need to put in time equals 0 and time equals 10 so that you can figure out how many gallons are in at those times and then do the whole slope formula, y minus y over x minus x. Okay, enough of that. Okay, next up. If I have a situation where, let's say, the position on a line, okay, and I don't know what the deal is with particles on the x-axis, but imagine I have basically a number line, okay? And here I am at 0. And let's say I have a particle that starts off at 1 on the number line, and it starts going to the right for a while, and then it starts going back, and it's doing that kind of thing, okay? So let's say I have an equation for this situation, and maybe it's something like negative t squared plus 4t plus 1, okay? So what I'm saying is the position of this particle that's cruising back and forth on a number line or on an x-axis, it's going back and forth, and anytime I want to know where it is, I just put in the time, okay? So I want to know, okay, a couple of things. Watching the time, sorry. I want to know how fast is it going at time equals, I'll go 2 seconds, and what direction. I don't know when it stops. So when does it stop? Okay, and then I guess that'll be good. Okay. All right. So how fast sounds like velocity or speed, but since I want to know direction, that kind of does tell me velocity. Okay, and I'm not asking where it is located 2 seconds in. I'm asking how fast and what direction it's going. So that's a vector quantity now, because we're talking about how fast is a number, and the direction is the other part of the vector quantity. Okay, so I need to do s prime. Okay, now this s again just means position. Where is it located? All right, so 2 times negative 1, so it's negative 2. T to the subtract 1 from that exponent to the 1 plus. Okay, 1 times 4 is 4. T to the 0, done. And again, the derivative of 1 is 0. Derivative of any constant is 0. Okay, so this is derivative. This is instant rate of change. This is velocity. I'm going to use this. This is not the answer, but this is what I'm going to end up using to answer everything else. Oh, no, this is just too easy. That's just wrong. Okay, so 2 seconds. Put that in. So I'm going to do s prime of 2 because I want to know how fast it's going at 2 seconds. So negative 2 times 2 plus 4. Well, that's 0. So what's that mean? It means I answered B also. All right, so how fast is it going at t equals 2? 0. What direction is it going? Nowhere. Yeah, that's the technical term for it. It's not moving. When does it stop? At time equals 2. Okay, so it stopped when the derivative equals 0. Now, you can tell I didn't plan this in advance because that was just too cute. Okay, let's just do one other quick one. Let's do at time equals 3 seconds. All right, so time equals 3 seconds. So again, I'm just doing s prime of 3. So negative 2 times 3 plus 4. That's negative 2, because it's negative 6 plus 4. And the units, well, it would depend on what it's numbered by. So I don't know what I don't know what units these are in. So you can just say negative 2 since there are no units here. If these were in centimeters, let's say, then this would be centimeters per second. Okay. All right, so negative 2. So what's that mean? It's going 2 centimeters per second to the left. Okay. All right, well, I want to stop here because this is pushing my time limit. It's, yeah. So, and we'll talk more about this in class. Okay, just a quick recap. Velocity is derivative of position. Acceleration is the derivative of velocity. And there will be more.